Alright, so just making a quick video here about the latest 3D printed object that I had Shapeways print for me. This was a totally new experiment for me on multiple levels because I was trying to do something that I've been wanting to do for ages with 3D printing, which is literally, in my opinion, the coolest thing ever about 3D printing, which is that you can do something with additive manufacturing, aka 3D printing, that you cannot do with any other type of fabrication that I know of. I mean, you probably could do this with casting, I would imagine, if you were like some kind of super genius and at the top of your game, but with 3D printing, it's a cakewalk to do this kind of thing. And so what I'm talking about here is putting a moving part inside of another part that's fully enclosed, that without any sort of seams or, it's solid state, in other words, except for this one moving part inside, which is inaccessible. I mean, basically, and here, let me demonstrate this. What's inside here is a little diamond-shaped turbine, which you can see spins very readily from either direction. It's a very simple mechanism. See if I can turn it. It's just a square, basically, on an axis that then has a slight amount of material removed from opposite sides to create a pressure differential, which allows it to spin when there's some kind of fluid, air, or liquid moving through the coupling. So how did I manage to pull this off, you might be wondering, without any kind of bearings, or like, how does it have such smooth turning? And let me see if I can give a quick illustration of this. I can find one of my whiteboard markers. Okay, here we go. So here's the turbine. Here's the different edges. Here's the axis. And now how this works is one of the most simple types of rotational mechanisms possible. We have is a sharp conical point here, which I'm going to just sort of like give a little perspective line curve on there. And then on the other side we have the wall of the cylinder coming along like this. And then there's a cavity in the cylinder like this, which is also a cone. However, it's a wider cone. So you have a sharp pointed cone in a nesting into a broader, not as pointy cone. So in other words, you have a lot of clearance here. Not too much, because this is actually incredibly tiny tolerances. So the whole idea behind this technique is that the point of contact is incredibly small here, which means that you'll get a fairly smooth rotation, sort of like similar to a bearing, without any of the complicated mechanical moving parts like a bunch of ball bearings, in the rotating cylinders. So anyway, it does work, and the cool part is that it's completely enclosed in the seamless cylinder. So like, there's no way to get it out. There's no way to take this apart without destroying it but it was printed all as one piece, which is just kind of, in my opinion, the coolest thing ever that you can do with 3D printing, because it's a real mystery for people who don't understand the process. So just for those of you who don't know, I'll do a little magnified example or blow up of this so you can kind of see what this would look like if you were to really zoom in. Because this is important in understanding how the process works in terms of 3D printing. So in reality, when these two parts, and they are two separate parts, the turbine and then the housing, are printed, what there is a minuscule gap here, like a really tiny gap, which you could only see if it was magnified. So right here, there's a little gap, and in the case of this particular material, that gap can be point, I think it's 0.0, I want to say 0.2 millimeters, but that's got to be way too tiny. So I'm thinking it's probably just 0.02 millimeters. So the gap is already there between these two pieces when it's being printed. However, there's a support material, usually like a wax or something, that is also printed in the space by the printer to hold these two parts together during printing. And I don't know all the details about how that works. All I know is that that material is included in the printing process to provide the support so the two parts don't touch and fuse together. And then when the part comes out of the 3D printer, there's some kind of thing that melts away that wax, or whatever it is. Sometimes it's a special resin, and then the part is able to move freely within the context of the case. So yeah, this part was initially designed as a visualizer for fluid flow from a tank to a pump. This is USA hose thread, which is actually horrible stuff because it is only used in the United States, and it's only used for garden hoses and garden hose accessories. I really think it should be done away with. We should just use pipe thread for everything, but what can you do? You have to design for the components that you're building around. So yeah, I made one major mistake when I designed this, and I think I learned the most valuable lesson from that, which was that when I re-engineered these threads for the more brittle acrylate material, I accidentally moved the center portion from the top of the thread where it was to the bottom of the thread, and what that did was it created a mirror image of the threads. In other words, they're reversed, and I had no idea that this was possible, but I learned from this print that yes, if you actually just change, you don't have to do any special flipping to the threads to reverse them. All you have to do is move your foundation from one side to the other, and it actually reverses them. And so these are mirror image threads, so it doesn't actually screw into anything because they're backwards, which was really annoying, but it was kind of cool just to learn that that was something you could do so easily without having to completely remodel the threads or flip the geometry or anything like that. And also something critical to look out for. I also did this sort of embossing of my SM with the date, which was kind of fun. I filled it in with some nail polish just to make it pop. It was cool getting to model this on the surface and to be able to model it precisely with all of the really fine details that like you wouldn't be able to do with PLA because the acrylate has such fine tolerances, which is really kind of a cool thing about it. Okay, so the success of this project that I was absolutely thrilled with was the turbine, that it actually worked exactly as designed, because I really wasn't certain that it would, but the motion is so fluid that even just moving it around can spin the turbine, which is pretty cool. So now I feel like more or less I have discovered how to create these moving parts inside an enclosed part, so I may use that technique in the future to do something even cooler than this. The turbine design is super robust, but it's actually not really a great design. Like, it works, but adding more dramatic curves, or adding something like this, like here's a profile view, and having like cupped sections like a Pelton wheel would have really helped to make it spin easier and smoother. Adding more blades, like 3 instead of just 2, could have been an improvement. Although, as you increase the complexity, you're also increasing the potential for failure. I don't know. Anyway, I just thought I would show you guys this model that I created because I thought it was kind of cool as a learning experiment. Oh yeah, one other failure I forgot to mention. This acrylate is supposed to, they call it frosted detail plastic. So like there are parts where, depending on how it comes out of the 3D printer, are optically clear because of the printing process. But for the parts that are not optically clear, they're frosted like this, so it's actually kind of like opaque. You can't see through it. Not like it's crystal clear, which was the only way this would have really worked how it was designed, because the whole point of having the turbine inside was that you could look through and see the turbine spinning as fluid moved through the coupling. And since it's opaque, you can't really see the turbine in motion. So that was something else that I learned about this material. Apparently you can use like acetone or something to melt the frost and create a crystal clear surface. I haven't tried that yet. With pure acetone, I tried like a diluted form of acetone and it didn't really seem to do anything. So yeah, just another factor of the design that I thought was worth mentioning. So wow, 13 minutes for this video, huh? I sure run at the mouth. Anyhow, thanks for watching, and yeah, let me know what you think.